So far we learned about what continuity is, and we learned about types of discontinuity. But all this discussion would be useless if you didn't know examples of continuous functions. So let me list functions that we know of that are continuous. The easiest ones are polynomials. Polynomials are always continuous. Okay, so think about like x cubed minus 5x plus 1. That's a polynomial, right? If you draw the graph, you'll see that it's always connected. Another one would be exponential functions, a to the power of x, right? So the functions that are exponential functions, the graph looks like this when a is bigger than 1, and if a is between 0 and 1, it might go down like that. These functions are always continuous. Now another example would be logarithms, log base a of x. However, you have to be a little careful because here x has to be positive, right? So this function has the domain that x has to be positive. For example, log a of 0 does not exist. And if you drew the graph goes like that, and you actually have a vertical asymptote right here at the y-axis. So it's not continuous everywhere, it's continuous on its domain. But what's the domain of the logarithms? It's continuous when x is positive. Okay, so let me write that down. Continuous when x is positive. Okay, next example. There's Sine X Cosine X. Well, in applied calculus, we don't care about these functions that much, but I just want to throw it out there that sine x and cosine x are continuous. And then, well, you have to be careful. Tangent, secant, these functions are not continuous because those have vertical asymptotes. For example, if you have tangent of x, the graph goes like, there's a vertical asymptotes here, and there's infinitely many vertical asymptotes. Yeah, but that's not too important. You don't have to write this if you're taking notes. You just have to know that sine x, cosine x are continuous, right? Now, number 5. After you have all these functions, then we can talk about rational functions. Rational functions are polynomial over polynomial. These are continuous if denominator is not 0. So let me explain this a little bit. So here is the graph of y equals to 1 over x plus 1. The graph has a vertical asymptote at -1, and it goes like this, goes like that. So this is continuous at x equal to a, as long as a is not equal to -1. See, at -1, there's a vertical asymptote, and the graph is not connected, right? It's broken. So in that case, we say that the graph is discontinuous at x equal to -1. So what I'm saying is that for rational functions, as long as the denominator is non-zero, then in those values, the function is continuous. Now we can further carry on and think about adding, subtracting, multiplying functions, and these will all give you continuous functions. So number 6, if fx, gx are continuous everywhere, right? then fx plus gx, fx minus gx, fx times gx are continuous. So as an example, you might have, say, e to the x. We learned that exponential functions are continuous. And you can add to this another polynomial, and that's continuous, right? Or you can multiply x plus 2, which is a continuous function because it's a polynomial, times, again, e to the x. That would be another example of a continuous function. So that's how you can get another continuous function. Number 7, you can also compose, so we're still assuming that f and g are continuous. F of g of x is continuous. Now, this thing here is often written as f circle g of x, and it's called a composition. Example of such would be e to the 3x minus 5 or whatever, okay? Now this is a continuous function because if you set f of x as e to the x and g of x as 3x minus 5, they're separately continuous, right? Exponential functions are continuous, polynomials are continuous, and when you plug one thing into the other, you get this function, and that's continuous. Now, some of you still have some trouble with composition of functions, so let me try to explain to you why these two functions, when you compose them, you get this. So first, I have f of x equal to e to the x, right? Now I can delete this, and say, what's this function? Function, whenever you put something, you're supposed to put it in here, right? And when you plug in g of x, the left side will be the composition, and the right side will be like this. But what is g of x? G of x is 3x minus 5. So if you plug in 3x minus 5, you have to plug in 3x minus 5 here so that you get this. So you can see that this is equal to this is equal to this. Okay, so that's why this is a composition of two continuous functions, and in that case the composition is continuous. Lastly, if you have fx over g of x, then it's like the rational function, but rational functions only allow top and bottom to be both polynomials, but here you may have like exponential functions on the top or some more crazy functions on either on top or bottom. So we're talking in more general terms. In this case, this is continuous when g of x is not equal to 0. Okay. So an example of this is, let's think about this function h, which is given by, say, x squared minus 5 over x minus 1 times x plus 4. Well, as long as the denominator is non-zero, it will be continuous. So this is continuous, except, it's always continuous, except at, when is this 0? When x is 1 and when x is negative 4. So those are the two exceptions, but otherwise this is continuous. So this shows how to make continuous functions from known continuous functions, and knowing such a function is such and such functions are continuous is going to be very handy. You'll find that out later.